In order to add and subtract vectors, we could use a geometric approach where if we had a vector v that we wanted to add to a vector w, we could arrange them such that the initial point of w is at the terminal point of v, and use either the triangle method to get the resultant, which in this case is v plus w, or we could arrange them where their initial point of v and the initial point of w are on top of each other and draw a parallelogram in order to get our resultant. And so if we did the parallelogram method, the resultant vector would be the diagonal of the parallelogram, and we would get essentially the same resultant vector either with the triangle or the parallelogram. But when we are adding vectors together algebraically, we can use the components of each vector to get a more accurate, precise resultant vector, one that does not depend on my ability to draw straight lines. So let's say that we have vector v, and here we're using boldface lettering to represent the vector. But we could also have the vector hat on top of v to be written, in this case we've got it in component form or as a position vector. I'm going to go ahead and pick up the position vector format of vector v and the position vector format of vector w. And so if we wanted to algebraically come up with the resultant vector instead of using the graphical method, we can add these two vectors together by simply adding the components. So we would add the horizontal components together to get the overall distance that we traveled in the direction of x, and then we would add the vertical components together to get the overall distance that we traveled in the direction of y. And when we add vectors algebraically, this is how we come up with the resultant. So the components of this resultant vector are the sum of the horizontal components and the sum of the vertical components. Now again, that is the position vector notation of this resultant. We could also write it in what we call component form, which would be that horizontal component, a1 plus a2, as the scalar multiple of the I vector, and the vertical component, b1 plus b2, as the scalar multiple of the j component. Now, just a quick note to say that these two forms of writing a vector, either position vector form or component form, cannot be mixed. So if you're using pointy bracket notation, then you should not have any i's or j's in these components. But if you're using component form, that's when you take the components and multiply them by the I vector and multiply them by the j vector. So two different forms that should not be combined. Algebraically subtracting vectors is much easier than graphically subtracting them, because as you'll recall, in order to graphically subtract, we had to find the negative w, or the opposite of w vector, and then arrange that vector either using the triangle method or the parallelogram method to come up with this resultant. But if we're doing it algebraically, all we have to do in order to come up with the difference between these two vectors is to subtract the component. So we would say, if we're doing v minus w, we would say a1 minus a2 is the horizontal component of the resultant. And then if we look at the vertical components, we would see that we're going to have b1 minus b2 to get the vertical component of this resultant vector. We can also write this vector in component form, where we have the quantity of a1 minus a2 as a scalar multiple of my I vector, plus the quantity b1 minus b2 as a scalar multiple of my j vector. Notice if I am writing in component form, I do not have any pointy brackets, but I do have i's and j's. And if I'm writing it in position vector form, I have only pointy brackets and no i's and j's. Now when we're looking at the scalar multiple of a vector, remember our vector v is given by a1 and b1, the horizontal and vertical components. Then if we're going to take that vector and either elongate it by a factor of alpha or shrink it by a factor of alpha if alpha is a fraction, we're getting a scalar multiple of that vector. And that scalar multiple is essentially going to have the components where the horizontal component is affected by that scalar quantity and the vertical component is affected by that scalar quantity. If we're going to shrink the whole vector, then we're shrinking the horizontal and the vertical factors or components by the same quantity, right? So it kind of looks like we're distributing that scalar multiple into the components of the vector. And again, if we wanted to write this vector as in component form instead of position vector form, pointy brackets is position vector, then we would say this is going to look like alpha times a1 is the scalar multiple of my I vector plus alpha times b1 is the scalar multiple of my j vector. So here we have position vector form and component form of that same scalar multiple of v. In order to determine the magnitude of a vector, we're going to use essentially the Pythagorean theorem again. So if we have a vector v that is given by a1, b1 in component form, let's remember what that means geometrically. I like to draw them from the origin so that the terminal point of the vector is going to match the components of the vector. And this is where we would say we can look at the horizontal distance that we've traveled, which is a1 in this case, and the vertical distance that we traveled to get from the initial point to the terminal point, which is b1. And now we can see that the magnitude of this vector is the same as the length of the terminal side. Well, that follows our Pythagorean theorem such that the magnitude of the vector or the length of the hypotenuse side is going to be given by a1 squared plus b1 squared. And so if I wanted to determine just the magnitude of the vector, we would simply just take the square root of both sides and get these components squared and added together. Now let's recall that when we're talking about the magnitude of a vector, that we do only want the positive values because we're talking about the length of that hypotenuse side. So when we take the square root of both sides there, we're only considering the positive output.